So today I would like to tell you about an idea from dynamical systems theory that may be able to explain and predict extreme events in weakly turbulent flow. So first of all, extreme events is somewhat of an umbrella term for behaviors that are infrequent, irregular, and often catastrophic in dynamical systems. So familiar examples of these events include extreme weather patterns, heart attacks, and seizures. And it is due to the catastrophic nature of these events that it is crucial we understand their mechanism and how to mediate these events. So the system that I'll be using to explore these events is going to be the 2D Kolmogorov flow. As you can see here, the flow is confined to a plane, and the forcing profile shears the fluid from left to right. So that's here. What distinguishes this setup from the Kolmogorov flows we've seen earlier in this session is that I'm using periodic boundaries, and this is a purely 2D flow. Similar to the Kolmogorov flows we've seen in this session, we are working in the turbulent regime. So extreme events in this system are characterized by global spikes in the dissipation, which you can think about as a volumetric average of the stress carried in the fluid. If you integrate this quantity for many time scales of the system, you see irregular spikes that deviate wildly from the expectation value. It is these events that we're hoping to describe. So it's going to be helpful for us to think about these processes both in physical space and in state space. So in state space, every flow field is uniquely mapped to a point in a very high-dimensional space. And then the dynamics of the flow traces out a one-dimensional curve in this space. What I'm showing here is going to be a low-dimensional projection in this high-dimensional space. I've singled out on the z-axis our parameter dissipation that describes extreme behavior, such that we can see in state space as well when this behavior occurs. To give you some intuition of what these events look like in physical space, we should notice that at the onset of extreme events, the flow field aligns with the forcing profile. What this does is it allows the forcing to inject a lot of energy into the system. This energy increases the shear in the flow, which of course causes this spike in dissipation. And as the system dissipates energy, it then returns to the low dissipation regime. Okay, so in dynamical systems theory, these turbulent trajectories, geometrically, are often thought about as a walk between the neighborhoods of special solutions called exact coherent structures. In this talk, it's going to be more helpful actually to think about the connections between these structures called heteroclinic and homoclinic connections. These connections are exact and bring you directly from one neighborhood to the next. These connections have been found in a variety of canonical systems and in between a variety of exact coherent structures, including equilibria, periodic orbits, and relative periodic orbits. And furthermore, these connections show a lot of promise in describing extreme behavior. In low-dimensional systems, these heteroclinic and homoclinic connections exhibit bursting. And in high-dimensional systems, such as the one that we're exploring here, Van Veen and Karaharwa showed that a homoclinic orbit in their plane Couette flow exhibited a large spike in dissipation along its trajectory. So in pursuing these kinds of structures in our system, we first ran statistics, and we said which states are most dynamically relevant in state space and which states are most correlated with extreme behavior. On the left here, you can see a equilibrium that we found and a traveling wave here on the right. These two states are two of the most dynamically relevant states in the low dissipation regime, and we found that this equilibrium is highly correlated with the onset of an extreme event. So if you see extreme behavior, it is very likely you saw this state just before. Given the dimensionality of the unstable manifolds of this equilibrium and this traveling wave solution, we expect there to be a 4-parameter family of heteroclinic connections between these two states. What I'm about to show you is all results in finding one representative member on this family of heteroclinics. Okay. So drawing from the extreme events that we see in turbulence, we use a variational method called direct-adjoint iterations to converge on a heteroclinic connection that begins in the neighborhood of the equilibrium, excurs into the high dissipation regime, and then lands in the neighborhood of the traveling wave. Qualitatively, we see these same behavior that we expect from extreme events in the physical space. Next, we want to ask, how helpful is this heteroclinic connection in describing the extreme events that we actually see in turbulence? And so to do that, we'd like to have some quantitative measure. So to describe the quantitative similarity of two states, right, we can define a distance between them. And so if you have some state u at time t and a different state v at time tau, we can just take their Euclidean distance. If we would like instead to describe the quantitative similarity of two trajectories, we can then compare, let's say, the heteroclinic orbit at time tau, heteroclinic trajectory at time tau, to the turbulent trajectory at time t. So each pixel here compares the distance between these two trajectories at each point. What you would expect in this kind of plot between two trajectories that are quantitatively evolving in a similar way is going to be a minimum of slope 1. And as you can see here, these two examples of extreme events from turbulence follow the heteroclinic connection that we found rather closely. I would like to point out that these two examples of extreme events from turbulence follow the heteroclinic connection up into the high dissipation regime and then deviate from it. We suspect that this is because we found a single member of the 4-parameter family of heteroclinics, and the behavior, once you're in the high dissipation regime, might be described by a different heteroclinic also in this family. So next we'd like to ask, does what we found here agree with what is seen in literature? So Farsman and Sapsis present evidence that the onset of extreme events is correlated to a dip in the magnitude of the Fourier mode 1,0. So what we've shown here is the magnitude of the Fourier mode 1,0 along our heteroclinic connection, as well as the dissipation along our heteroclinic connection. What we find is that the magnitude of the Fourier mode dips below the trigger threshold value as the dissipation of our heteroclinic connection exceeds the threshold for extreme behavior. So this is in agreement with the results of Farsman and Sapsis. So I'm ending a little bit early here, but I'd just like to conclude with what we've done is that we found a heteroclinic connection in Kolmogorov flow that connects two dynamically relevant exact coherent structures in turbulence. We then found that extreme events in turbulence make close passes to this heteroclinic connection. What this ultimately shows is that heteroclinic connections may play a very important role in describing extreme event production in this system as well as others. I would like to acknowledge some of my colleagues for this work, specifically Mohammed Farsman and Dmitry Zhuganov for sending me exact coherent structures in this flow, and Balakandar Shuri for his help with my coding. All right, thank you. Any questions? Yes?
Can you say something about what are the properties of these precursor states? I mean, you show this state that we're going to blow up. How do you know that it's going to blow up? Can you say that?
How do we know that this is going to exhibit extreme behavior?
Or which are the properties, the general properties that
yeah. So I'm not actually sure about the states themselves, but the way that I tend to think about something like that is sort of in terms of the work that has been done looking at maximal perturbations, right? So given the structure of the unstable manifold, it's not always clear the perturbations that cause the behavior you're trying to see.
I mean, something like from a practical point of view, when you see these around for forward, because
right. So I guess I haven't really found anything that distinguishes this state in terms of producing extreme behavior, but the initial point of this manifold, so more this region here seems to be more correlated with the extreme behavior. That makes sense.
So basically, you cannot really tell from the structure of the state necessarily that extreme event is going to follow. of the structure of solutions that lie with unstable manifold of that state
Yes, but
is
you have to
cyclical
compute
manifold.
it. And the question is whether from that system you can link it to.
Maybe not.
Right.
Right, so the structure of the predictor state may not fit a whole.
And so our hope is to actually flesh out this 4-parameter family of solutions instead of.
It's not something like this, they have a very unstable eigenvalue.
No, so this one has 4 eigenvalues that are roughly of the same order of magnitude of stability.
Right.
And other unstable eigenvalues that are less unstable. Other questions?
Can you tell us more about the variety of different extreme events that you see? As you get more and more extreme dissipation, do you always get more and more the same state, or are there a class of different states that are up there?
So I like to show this plot to kind of elucidate that. So it seems that the dissipation has a lot of different profiles, right? But seemingly, they all seem to be described, at least in their initial segment, by the heteroclinic connection that we found. So we suspect, if we look at and think about this 4-parameter family of solutions, that there's going to be a very sort of close, narrow width here. The behavior is going to be very similar. And then the trailing end is going to be very broad and exhibit very different behavior. But nonetheless, we believe it should terminate in this traveling wave solution. And so that's why we suspect that our heteroclinic only described the initial trajectory into the high dissipation regime and not the trailing edge.
Another question?
Is there something particular about the one you found that stands out through the 1-parameter family of solutions or multi-parameter family of solutions?
Not necessarily. I'd like to have other solutions from this family in order to kind of make statements like that. It is potentially one of the more dynamically relevant members of this family, given that we found it from an example in turbulence and then converging.
Oh, I see.
But yeah, until I find more members, I can't really quantify that any better.
But now that you found one, you can maybe continue it.
Exactly, and that's what we're hoping to do, is now step slowly and fill out this entire family of solutions.
The last quick question.
Okay. Yeah, it's very interesting. To me, it kind of suggests also an application to control, in the sense that if you know one of these trajectories, you might want to construct a kind of forcing or intervention that disrupts them, right?
Absolutely. So that's ultimately the hope of this, is now that if this can be the mechanism for extreme behavior, we can find ways to control this and inhibit it in the systems that we observe them in. All right, thank you.
All right.